Hello everyone. So it's time for our final lesson in the trig unit, section 5.6, cosine law. So we did sine law before, we got cosine law now, and good or bad news, depending on how you want to look at it, there is no tan law. So this is it for was. Okay, let's just jump right into it. So we're going to derive cosine law. What cosine law is it's an extension of Pythagoras' theorem. So you remember, a squared plus b squared equals c squared. Well, we're going to extend that to triangles that are not right angles. So it turns out Pythagoras does work for all triangles. It just it's a special case where it simplifies down for a right angle. So here's the derivation. So this one's a little trickier than the sine law one, but I think it's worth looking at. So just like with the sine law, you've got a triangle here, ABC, and it's laid out in this way. And what we're going to do is we're going to draw this vertical line going up, straight up like this. So what I'm going to do here is I'm actually going to give this a couple labels here. I'm going to give this y because it's in the y direction, and then this part right here, I'm going to make this x. That means that if this entire length here was a, then the little bit left over here will be a minus x, and that's going to be important in just a sec here. So when we're deriving cosine law, we're going to start with the basic idea. If this was a right angle triangle, it would be really simple. We would be able to say c squared equals x squared plus y squared. Now it turns out that we can modify this a little bit for a non-right angle triangle, and I'll show you how. So the first thing we have to do is we have to realize that we've constructed two right angle triangles here. Now it turns out that where I'm going with this is I want a cosine law, and I want it to be in terms of angle capital C here. So I'm going to write a whole bunch of stuff in terms of capital C. So the first thing I'm going to do is I'm going to, I don't actually want x and y, I'm going to replace those. I'd rather have a's, b's, and c's because that's what we were originally given. So what I'm going to do is I'm going to write this. I'm going to write that sine of capital C is equal to opposite over hypotenuse. So this will be y over b. And I'm also going to write that cosine of capital C is equal to, so now I have to do the adjacent side. The adjacent side is a minus x, and that doesn't look like it's going to be very good, but don't worry, it'll all work out. And then divided by hypotenuse, which is b. So I've got sine c equals y over b, and cosine c equals a minus x over b. So what I'm going to do is I'm going to move things around. So I'm going to multiply the b to the other side to get y equals b sine c, and I'm going to multiply the b to the other side to get a minus x equals b sine c. Or I can do a little switcheroo, and I can get x equals, take x to the other side, we'll move this over here, a minus b sine c. So all I've managed to do here is I found ways to rewrite x and y in terms of things that are given, which is a, b, and c. So I can go up here to my Pythagoras equation, and I can write, instead of x squared, I'm going to write a minus b sine c squared. And instead of y, I'm going to write b sine c squared. Okay, so if you're wondering where I'm going with this, this is going to get ugly, but I promise it will clean up, and there's a couple neat little identities that we can actually use to clean this up really well. I'm going to give myself a bit more room because I think I might need to jot some things down up there. And in fact, the first thing I'm going to do is I'm going to just do this. I'm going to write it up here just so I leave myself some room. A minus b sine c squared. Okay, so we have to FOIL this out, right? So the first term is going to be a squared. And then when we multiply this in with itself, we're going to get 2ab sine c. And then, oh, crud, I made a tiny little mistake. So those of you sitting there going, you made a mistake. Yeah, there we go. Okay, so I had sine. This was actually supposed to be cosine. Whoopsie doodle. Sorry, when I was rearranging this, a minus x equals b cosine of c. There we go, cosine. Okay. Everything's right with the world now. If you were yelling at the screen, what is that guy doing? Well, there we go. Okay, so that should be cosine, because we started with cosine up here. Okay, so what we have is we've got a squared minus 2ab cosine c, and then the last term will be negative b cos c times negative b cos c, so it will be positive b squared cosine squared c. Just a quick little thing for you if you know this. Cosine squared c is the same thing as cosine of c all squared. It's just a nice cleaner notation in trigonometry, so just be aware of that. Okay, so that's the expansion of this first guy here. So this is going to expand out to a squared minus 2ab cosine c plus b squared cosine squared of c. The second term, b sine c all squared, that's easy. We're just going to distribute the squared into the b and the sine c. So it's going to become plus b squared times sine squared c. All right, so if you are still with me, that's fantastic. If you're just kind of going, what the heck did it do? I just did a bunch of expanding in algebra. Feel free to go back and look at it again. But it's not even super important. I just really want to show you a couple of these steps in deriving cosine law. So what we're going to do here is we're actually going to do something pretty nifty. Now, at some point, I think this might have been one of the homework questions. If you encountered it, great. Sine squared of an angle plus cosine squared of an angle. What's that equal to? What's that you say? 1? You're right. It doesn't matter what the angle is. It's a really neat fact about sine and cosine that sine squared of an angle plus cosine squared of the same angle will always equal 1 no matter what the angle is. So why I'm mentioning that is because if I go here, I'm going to leave these first two terms the same, but I'm going to factor out a b squared from these last two terms. So in brackets, we get cos squared c plus sine squared c. What's so nifty about this is cos squared of an angle plus sine squared of an angle is always equal to 1. So this is just 1. It's basically like it's not even there. And this ends up with a nice little result. C squared equals, I'm going to rearrange the terms just because I like them in alphabetical order. A squared's there, b squared, positive b squared or plus b squared, and then we've got minus 2ab cosine of c. That looks an awful lot like Pythagoras, but with an extra little something something there at the end. And that is what cosine law is. So this is cosine law. Hooray, ta-da, we're done. That actually wasn't too horribly difficult, just a little bit of work. Now, I'm not expecting you to necessarily reproduce this derivation here, but I hope you can at least appreciate a little bit of what it's about. Just a little note on this minus 2ab cosine of c. Think about this a little bit here. Now, if this was a right angle triangle, so if c was 90 degrees, what would cosine of c equal? Like, let's say your triangle actually looked like this. Here's B, here's A, here's capital C, that was 90 degrees. What's cosine of 90? Turns out that's equal to, and here's your graph, right? You did this in an assignment. Here's 90 degrees. Cosine of 90 is 0. So if you actually have C being 90 degrees and it's a right angle triangle, what happens to cosine of C? 0, and this term disappears entirely. So you can see that Pythagoras is just a special case of the cosine law where you have one 90-degree angle. If you have an angle that is bigger than 90 degrees, what might you expect would happen to C, the hypotenuse? It looks like C would get longer, right? As this angle here gets bigger than 90, C should get longer. And what happens if you have cosine of an angle bigger than 90? Well, all students take calculus. Cosine of an angle larger than 90 will be in quadrant 2, but the cosine ratio is negative. So this guy becomes a negative number for angles larger than 90. What's interesting about this is when you go minus 2ab cosine c minus 2ab times a negative, you're actually adding something to it. So the calculation for calculating the hypotenuse is to go a squared plus b squared. And you're actually adding a little extra something something here. So when when the angle for c is bigger than 90 degrees, you're adding something which makes little c, the hypotenuse, bigger than what it was before. So that should make some sense. And you can also say that if the angle was less than 90 degrees, like you had your triangle, except capital C was less than 90 degrees, then you'd expect the hypotenuse to be shorter than if it was 90. And that should make some sense too, because if the angle's less than 90, then the angle's in quadrant 1, and cosine is positive, and you're going minus 2ab times a positive number, so you're actually subtracting. So that might be a little bit more information than you're ready for if you've just heard about cosine law for the first time right now, but it's something worth thinking about. The way I kind of figure this little extra bit, this is almost like the correction factor here. It's the correction factor to say the hypotenuse gets a little longer, gets a little shorter. Anyway, it's got lots of connections, so there you go. Okay, so in fancy pants, formal math type font here, there's cosine law, c squared equals a squared plus b squared minus 2ab equals c. Now it turns out this could get rearranged in different ways as well, because you didn't have to go ABC, you could have went CBA, and you could have reproduced the whole derivation. The thing I will mention is this can be rewritten as a squared equals b squared plus c squared minus 2bc cosine of a. And you could also write b squared equals a squared plus c squared minus 2ac cosine of b. The big thing here is that we have to make sure that this letter here and this match up. So if that's an A over there, then this is a capital A, and if this is a B, then that's a capital B. And the other thing I'll mention is that, oh, that's probably going to be too dark. If there's B and C here, then it's going to be B and C there. If it's A and C here, it's going to be AC there. And if it's A and B, it's going to be AB over there. Okie dokie, so there we go. So that's cosine law in a nutshell. Now, what can we use this for? This is really handy when we have an angle and we would like to know the side across from it. So I'm just going to write a tiny little note. Useful for solving. And there's a special name for this kind of triangle. It's when you have a side and an angle in between. You don't say side-side angle, you say side angle side. The angle is between two sides. So we're going to be solving those kinds of triangles. Contrast that with sine law, where sine law, remember, sine law was good for SSA triangles, where you have two sides and an angle, but the angle's not sandwiched in between. So anyway, we'll be looking at this a little bit more in the examples. So example 1, determine the length of side x. So the first thing you're going to do is you're going to look at this triangle and you're going to give it some labels here. So I'm going to call that A, B, C, I'm kind of doing it randomly. So that means this is side A, this is side C, and this is side B. You also identify this triangle as having a side and an angle and a side, and the angle is sandwiched between the two sides. So because this is an SAS triangle, it's sassy, we're going to use cosine law to solve. That's where it tends to be better. Remember, sine law requires you to have an angle and a side pair. So if we know 17, we don't know C, that's not a good pair. We know 45, but we don't know X, that's not a good pair. And we know 16, but we don't know B. We have no side angle pairs. Sine law is absolutely useless for this. So what we're going to do is we're going to go cosine law. Now, the way I've labeled it, A, B, and C, I know angle A, so the way I'm going to express this is I'm going to go A squared equals B squared plus C squared minus 2BC cosine A. If that upsets you and you would have preferred that I called this capital C, you can go ahead and do it, but I just want to show this formula, the notation's pretty flexible, just as long as this and this match up. Okay, so how do I actually solve this? It's pretty easy. If I want to know the side length of A squared, I just put numbers in. It's basically just a formula from here. Nothing too tricky about it. So we'll go 16, 17, we'll go cosine of of 45. Okay? So all we do is we go to our calculator here, so we make sure the thing is turned on. Make sure you're in degree mode, and then we'll go 16 squared plus 17 squared, and then minus 2 times 16 times 17. You don't even have to write multiplied by cosine of 45. I like to close up the bracket just to be safe. You do this. Now you realize you just calculated what a squared is equal, so a squared is equal to 160.33, blah, blah, blah. And of course, don't forget to square root it. So the way I do it on this calculator, I go second to get the root, and then I go second to get the answer, and I push equals, and I get the exact value for a. We're not going to worry about plus or minus here, when you square root a number, just because it doesn't make any sense. So let's say it's about 12.7 centimeters. There's no such thing as a negative number there. Okay, so that's using cosine law. It's pretty simple. As long as you label it and you put numbers into your formula and hit your calculator correctly, life is good. Let's do the next example here. Three sides of a triangle are given. Determine all the angles. So in this case, this is an SSS triangle. This is also somewhere where you would use a cosine law. Because sine law, again, we have no angle side pairs. We cannot use sine law for anything here. We have too many unknowns. So cosine law will solve this for us. So again, I'm going to go A, B, C, and that makes this little c, this makes this little a, and this is a little b. So what we need to do is we got to figure out some angle here. If you want to figure out angle A first, go for it. B first or C first. I'm kind of liking the original form of the equation more because this is what I'm used to. So I'm going to write this down. And what this is going to allow us to do is solve for angle C. So once we solve for angle C, then we can do some stuff. So my advice to you is pause the video and actually try and carry this out yourself and make sure you can do it. Typing it all in on a calculator is not that hard, but it's also not super trivial. It sometimes takes a little practice to make sure you get everything right. I would also recommend rearranging first. Okay, so what this answer will look like here, well, we're not quite at the answer yet, but let's just set it up. So C is 15, A is 10, B is, A is 13, B is 10. That's why I was having a small stroke there. Okay, so here's 13, here's 10, and then of course we've got cosine of C, which is our unknown. So the way we do this is we're going to take these guys, we're going to move them over to the other side. So this is going to look like 15 squared minus 13 squared plus 10 squared equals negative 2, 13, 10 cosine of C. And then we're going to divide both sides by negative 2, 13, 10. So this will become 15 squared minus 13 squared plus 10 squared over negative 2, 13, 10 equals cosine of C. So at any point you can go ahead and calculate that. I'm going to show you what I'm going to do on a calculator to work this out. I'm going to say C is equal to the inverse cosine of, and then all that stuff. So that's 15 squared minus 13 plus 10 squared over negative 2, 13, 10. Okay, so I'm going to actually do this all here. So I'm going to go second function, cosine, and then I'm going to go 15 squared minus 13 squared plus 10 squared. Okay, now this is where you got to be real careful here, actually. So make sure you put brackets all around. If you want to be really safe, in fact, this is maybe the way I would recommend it. I actually kind of like to work out the numerator, so I'm just going to push equals. Then I'm going to divide it by, in brackets, negative 2 times 13 times 10. Close it all up. You have to use brackets there, otherwise it'll just divide by negative 2 and then multiply by 13 and 10. So I get this, and then I go inverse cosine of that answer, and this is probably the safest way of doing it all. And I get an angle of 126. So that's where I sit there and I'm going, okay, that's interesting. Now here's the funny thing about this. I feel like I might have made a little boo-boo somewhere, because why am I getting 126.869 degrees? That seems a little too big. In fact, if you look at this triangle, I don't really think I should be getting a large angle like that. It looks like it should be less than 90. So there's two ways I can go about approaching this, and I think the way that I'm going to go about approaching this is what I did is I took inverse cosine, and I took inverse cosine of negative 0.6. So one thing I want to make sure that I'm not screwing up here, and I realize I made another mistake. Boy, I'm really on my game today. Okay, so this didn't seem right here, and I apologize for making you watch me do another silly mistake. I'll try and be a little more careful. Up here, see this 13 squared minus 10? That's supposed to be a plus, which turns this into a negative, which turns this into a negative, which changes a whole bunch of stuff. Okay, so maybe what I've done, if anything, aside from making a dumb mistake, is I've proven to you that if you get something weird like 126, something ain't right, because this certainly doesn't look right. So I'm just going to go back here. I'm going to retry this. It should not have been like that. I should go 13 squared, and I should go minus 10 squared. There we go. And then when I divide that, I'll divide that by negative 2, which is, and then multiplied by 13 times 10. It's actually very rare, if even ever, that you're going to wind up getting a weird answer like that when you use cosine law. So when I actually work this out, there we go. That looks much better. Okay, so if you get something larger than 90 degrees, you probably did something like what I did, and you done screwed up there. Okay, so 80.26, that angle in there, that actually looks pretty good. I realize triangles aren't always drawn to scale, but this one looks pretty good. And also, if you're wondering, no, there is no ambiguous case of cosine law, and no, I don't have to worry about that thing like in sine law, where it's very possible I get, like an obtuse angle. I got to go think about the reference angle versus the real answer. That stuff actually doesn't exist, so you should be expecting to get answers more like this. Now, if you're wondering, is it even possible to get an angle bigger than 90 using cosine law? You bet. But with cosine law, you can pretty well trust your answers. As long as you do the work correctly and don't screw up your positive signs, you're going to get the right answer right away. So it's a lot safer than sine law, but it's a lot more algebra. Okay, so there we go. Moving on from that little mistake, how do we get the rest of our angles here? So we can now, if we want, we could repeat that exact same calculation where we could use angle B in there, and we could do it for angle A if we wanted. But I actually am a bigger fan of using sine law because it's a lot less algebra. So I'm going to now use sine law to find B, because now I've got a side angle pair. So I'm going to write sine C over little c equals sine of B over little b. So this becomes sine of 80.26 over 15 equals sine of, I don't know what B is, over 10. Solving this, I'll get B is equal to, so I'm going to move the sign over there, so it's inverse sine 10 sine 80.26 over 15, and then I should be able to get my answer that way. So I'm going to go inverse sine 10 times sine of, now I've got 80.25, so I'll actually just use that because that's my answer. Close that up, and I'll divide it by 15. Close the brackets, and I get myself 41.07. So 41.08, I guess rounded up. Does that look like that's approximately correct? And I feel pretty good about that answer. And of course, finally, then I'll go, so there's B, and then I'll go A. If I'm confident in my work, which I am now, after looking at my mistakes, I will work out the remaining angle by just going 180 minus all that. So 180 minus all that business. Oh, I could try and do this in my head, but seeing how I've made 2 dumb mistakes so far in this video, I am going to just use my calculator and be very safe. Okay, so we wind up getting this, and we've got 58.66, so I'll say about 58.7 degrees. And that looks like that could be reasonable, 58.7 degrees. Okay, so that's my 3 angles there. Cosine law can sometimes unlock, I guess, a side angle pair, so you could use sine law, and then you can go 180 minus that. So those are the main types of questions that you'll have. The big thing for you will be deciding when to use sine and cosine law. Sometimes you can use both, sometimes one is better than the other, and it's all up to you. Okay, so we have some more examples. I'm actually going to leave that for a second part because we're going to talk about bearings where we have directions and then some word problems. So I'll leave it here, and then that is the lesson for today. Next time, part 2. See you later.